Hi, everybody, and welcome to this edition of the Taking Control of Your Diabetes podcast. I am one of your hosts, Dr. Jeremy Pettus, joined as always by my good friend and colleague,
Dr. Steve Edelman.
So, Steve, what are we talking about today? So we were talking about something called islet cell replacement therapy. What does that mean to you when I say that?
You know what that means to me? I've had diabetes for a long time. So have you. And this is technology that will help restore the beta cells that were destroyed when I was 15 years old by those frickin' autoreactive T cells.
Yep, still mad at those T cells. So that's exactly right? So if you don't know anything about type 1 diabetes, you know that people with type 1 don't make enough insulin. And guess what? That insulin comes from the beta cells. And basically, to try to kind of cure this disease, we've always been looking for ways to give beta cells back to people with type 1. Steve, you and I maybe have like one or two hanging around, but we could use a lot more. So this has been like work, research, clinical trials that's been going on for decades in terms of how do we give people with type 1 diabetes beta cells back so they can make insulin, so we can throw away our pumps and CGMs and all those things. So this has really evolved over time, and we're going to get into the specifics of this when I introduce our very special guest today. But this has evolved from transplants of actual pancreases to now when we say islet cells, it's how do we take just specifically those cells of the pancreas, of the whole pancreas, less than 1% of them are beta cells. We don't need a whole pancreas. We need just those cells. But how do we find the way of getting those cells? How do we give them back to people? Where do we put them? What do people need in terms of immunosuppression? All those things we're going to dive into today. So Steve, do you want to introduce our guest?
Well, I would say one more thing, and then we'll introduce our esteemed guest. One thing people forget about is that when you and I got type 1, you know, our beta cells are destroyed, and currently those auto antibodies that destroyed our pancreatic beta cells are still there. And that will relate to the technology that Manasi Jaiman will tell us, who is a pediatric endocrinologist, super active in this field, originally went to work for ViaCyte, and which we'll talk about that. And then ViaCyte was purchased by Vertex, which is a huge company working on this field with many different trials going on. And so we're excited to have you here.
Thanks for having me.
Yeah.
I'm excited to talk about this.
And no stranger to our podcast, by the way, or TCOYD in general, done a number of videos with us over the years and did one of our first podcasts we're remembering. So you can look back. It's called For Parents of Kids with Type 1 Diabetes. So check that out. So Manasi, remind the viewers of who you are, your story, and how you met us, I suppose.
How did you end up at this podcast table?
Yeah.
Hey, I got paid a lot of money. No, I'm kidding. No, I've been following you guys even before I moved to San Diego. And I moved to San Diego to work at ViaCyte. I was their chief medical officer. We were acquired by Vertex. I've been really fortunate to work in a space that I care so deeply about. As a pediatric endocrinologist, I left Boston, and I promised my patients that I wouldn't give up until we were closer to a cure. And that's why I'm here. And that's actually how I got involved with you guys as well. I followed you. I told all my patients to watch your videos back in the day when I was still in Boston. It was so innovative. So obviously I'm a fan. But I also knew I wanted to be part of those videos at some point. And I was lucky enough to meet you and be able to do that. So thanks for having me then and now.
Well, I would say that folks may not realize, the listeners may not realize that Jeremy here was involved in the ViaCyte implantable islet cell project and recruited the first group of patients and followed them right through the emergency room, through the operating room, and followed them to this day. And that was 10 years ago.
Yeah, I was just thinking about that. I was doing a little bit of Googling in terms of the first time we ever transplanted a pancreas in somebody was like the 1960s. Yeah. The first islet cells that we took and infused back to people was in the early 2000s, 2004. And then, here in San Diego with myself, the first implant of these stem cells we did was in 2014. So 10 years ago, and little old me was, the first, person to do this. One of like the first patients that we recruited were friends of us, friends of TCOYD. Mm-hmm. And so here we are now, 2024, and it's time to kind of take stock of where we are in this field, but also reminding people, what are stem cells? What are islet cells? What are these transplants? How does that work? So that's kind of our first question to you, Manasi, is, how do we give beta cells back to people? How do you think about all the ins and outs of that question?
It's a big one.
Yeah.
I'm going to start off with a bang. Okay. When I think about beta cells and what that means, so it's not just beta cells because it's part of the bigger picture. You need islets. So when people think about cell therapy, you have to think about islets. So when you talk about islet transplants in early 2000s, islets encompass all the hormones that are really required for that balance for your blood glucose: insulin, glucagon. And the cells that are within an islet, beta cells and alpha cells, which make glucagon, are both extremely important to work together and synergistic. So it's not just beta cells, it's really islet cells. And there's different versions of companies that you might hear about that work on just beta cell infusion. But for what I know, you need both. You need both hormonal regulations. And so when I talk about replacing beta cells, it's beta and alpha. And I will always use islet cells. And I think that's the right word here. In terms of islets, where we've been, I'm very careful about the words I use here. And that's because I think about patients first and foremost. I think about the patients that I left back in Boston to promise this cure. And it's a promise, and I cannot call it a cure yet. There is a bit of hope attached to that, and you have to be realistic. But we've come so far in just 5 years. But can I tell you that it's around the corner? No. I can tell you that we're inching closer. And it's through the research and the people that are involved that we're able to get so close to what we're trying to accomplish for people to change their lives. But it has to be a realistic approach. Mm-hmm. That's the first thing I'll always start with.
Well, that's important because, Steve, you were diagnosed in what, 1936? 1970? And
thank you.
And how long were you told it would take to get a cure?
10 to 15 years.
Yeah.
Mm-hmm. And I was diagnosed in 1994, and I was told 10 to 15 years.
Yep.
And if you were diagnosed in 2022, it was probably 10 to 15 years. And now, when people ask me, I still say 10 to 15 years.
Yeah.
But I think it's probably a little bit more realistic.
Yeah. I think I would say that if you said to me right now 10 to 15 years, I would say, okay, that's probably around the ballpark.
More realistic.
Than we've ever been. And only because of what the field's doing now. The companies that are in it, the clinical trials that are there, the results we've seen all point towards that. There's still a lot of work to do. So we're going to get into that.
All right. So, we're talking about we need islet cells. We need to give them back to people. Where do we get islet cells from?
So their islets are donated through a donation process of pancreas that have been donated by deceased patients. And we actually can harvest islets from them, and that's what was done in the early 2000s. So that was through the Edmonton protocol. You can read all about it. And that's really the foundation of the current clinical trials.
But this relied on organ donors, essentially.
And it's always organ donors. And the problem with that is quantity and quality. So you can find donations, but then you can't harvest all of those cells, meaning take those cells out and make them usable. And so that limits your ability to access any of the islets. So that's one of the problems with islet therapy in itself when in the early 2000s. What we've come to know now is a different version of this, people being able to create cells that can be differentiated into beta cells, alpha cells, the full islet.
And so that's where stem cells come in.
That's where stem cells are.
That word is so loaded.
It is.
So if someone asks you, what is a stem cell as it pertains to islets? How do you answer that question?
So I would say stem cells are basically immature, undifferentiated cells in the body. You can get them in different variations, but I can talk about that in a minute. But basically undifferentiated, they haven't been specialized, but they can be programmed to be specialized based on multiple factors.
Well, the whole stem cell, being able to produce them ourselves, takes away the religious and political aspects of, taking human placenta and going from there. So, and it also allows a ton more to be able to take someone with type 1 and get them off of insulin, whereas you harvest them from cadavers and there's just not enough.
Well, I think that's an important point that Steve's making, that people hear stem cells, they think these are coming from human embryos and abortion and all these things come to mind. But tell us about these cells. These are cells that have been around for a long time that you're able to kind of grow them in perpetuity without actually going back to embryos, all that. I think that's important to understand.
So there's three kinds. First, there are the embryonic stem cells. And so those are actually donated embryos, early stages of development, very, very early. And then they are procured and then differentiated to different stages and used. And the reason they use embryonic stem cells really is because they have the most potential to differentiate into whatever you need them to be in the body. Then you have adult stem cells. Adult stem cells I can give you an example. In our gut, there's turnover every few days of the intestinal lining. There's stem cells behind that lining that are solely made to be intestinal stem cells and become into various cells that are surrounding our walls. But they're already pre-programmed. And so those are adult stem cells. They can't be as specialized or as we want them to be with embryonic, but they are available to differentiate into the very specific tissue type. Then you have induced pluripotent stem cells. This is where it gets a little wonky. So you have iPSCs. Everyone's going to hear that in the cell therapy space because it's out there. So you hear stem cells and you hear iPSCs. What are iPSCs? iPSCs are basically induced, meaning they're induced from an adult stem cell line. They've been changed, reprogrammed to behave like an embryonic stem cell. So that's what you're talking about, Steve. That takes the element of the controversy from embryonic cells, and you're using adult stem cells that have just been donated. And it could be your own autologous cells.
So then correct me if I'm wrong, but then the current approaches with islet cells and stem cells in type 1 diabetes is these cells that can be grown in perpetuity. We're not going back to the embryos. The advantage is we have these cells that can actually overcome the huge obstacle of relying on organ donors. Mm-hmm. Now that we can essentially grow enough of these cells in a lab to treat everybody with diabetes.
Mm-hmm. You just need one donation.
Yeah.
One embryonic stem cell line can have unlimited supply.
Yeah.
One adult cell donation, because it could be from someone else that you're getting this from. But remember, all of these, it depends how you infuse it. It depends. I know we're going to get to this too, Jeremy, but it depends how you place it in the body. Yep. There's also repercussions there.
And I've heard people when they talk about these stem cells, to really kind of put it in lay terms, it's like baking a very sophisticated cake. That you take these cells that could become anything, and day one you have to add this ingredient and that ingredient, and you coax them along the way to say, hey, I want you to become islet cells, beta cells, alpha cells. And I think it's helpful for our listeners to understand that that's kind of how these work.
That would be a funny video.
Yeah.
We could pretend we got
you and I with those chef hats on.
We coax them. Come on.
I love it. It's like baking. It is. And it's like a sourdough, right? Sourdough. Everyone during COVID, I don't know if you guys knew, they always had the right like sourdough recipe and they had to wait for days for the right thing to happen. Same thing here. You mean you have to wait for days for things to mature into the right bake.
All right. So you're right. So let's say we've got it down. We've got the way to take these stem cells. We can make a bajillion million islets. Yep. How do we give them back to people?
Different ways. Okay. So this is placements, the third P I was talking about. So islet transplants, early 2000s, they were infused through the portal vein, through your liver. And that's traditionally how the infusions are done now, even with the cell therapy that we have. But there's also encapsulation. So that's a popular term used. There's lots of companies in the space now trying to figure out how to keep cells in a little device and then implant it in your body.
So that they don't get attacked by those autoantibodies that cause you to get diabetes in the first
T
place.
cells. You really have it out for these T cells.
Really hates them.
Well, you call them killer T cells.
But
they are killers.
I do too. I kind of don't like them.
But and that's the whole issue. I mean, if we can produce these islet cells, as many as we want, how do you get them to live in the body? And that's what we're talking about now.
So some things that haven't changed from from pancreatic transplants to islet transplants is the immunosuppression. Our bodies are very, very smart at getting rid of foreign particles. And so these cells that are donated, they're not yours. They're donated from someone else, something else. And when you put them in your body's first response is to attack because they don't belong there. And immunosuppression has been around for a long time. Now, there's many different versions of it. It's a lot safer. I think what we know of is what's from the 60s and the early 2000s. But I think what we need to discuss now is that they're so much safer to use. And they are used because if you're putting cells in your body without having a device surrounding them to protect them from that attack, cells will attack them. So you need to take immunosuppression. But the other way to offset that is the device or a pouch or anything that encapsulates the cells and shields them basically from being attacked.
And I've always said, like, a great thing about islet cells is they don't need to be in the pancreas. It's just kind of whatever evolution or whatever that they got put there. And it's kind of a really hazardous place for them to be honest, because the pancreas is full of digestive enzymes, and it's like being in a swamp. But
that's a good image.
Never heard that description. Don't call my pancreas a swamp.
Well, you don't have any islet cells, so they're not in a swamp. But anyways, that actually made you sad. So they just need to be able to sense glucose, let's say, and respond with hormones. So you just need to put them someplace that they can have a blood supply. And that's very different than saying you need a heart transplant or a kidney transplant where you actually need it to go back in kind of the place it's supposed to be. Islets, you could potentially put them in many different places. So we have an opportunity to put them in some kind of device. I've always said, like let's say a plastic type coating or something. You protect these cells and plant them under the skin or wherever we might want to put them so they get a blood supply. But the idea would be that would be a less invasive surgery. Let's say it's underneath the skin. You might not need immunosuppression if you can really just kind of wall these things off. And as long as they have a blood supply, they could sense glucose, respond with insulin, glucagon. So you would have a functional pancreas that you could implant kind of in different places with the goal, the kind of pie in the sky being a very easy to do procedure for the masses with no immunosuppression. That's kind of the ultimate goal.
Oh, absolutely.
Yeah.
And
couldn't have said it better.
Let me ask you this, Muncie, and you too.
Thanks, Steve.
Jeremy.
Okay.
10 years ago, ViaCyte started the encapsulation. And you know what? It's a tough technology to succeed in, and they learned a lot from it. But where have we come from there? And where are we today? Because I know Vertex is doing the 880 and the 264 studies.
So we've come a long way in terms of our understanding. I will say that. There's still a lot more work to do in the encapsulation space. Now, what I will say is infusion studies in the clinical trials right now, we're infusing cells. Vertex, we've seen the news, lots of success there. And that's what we're looking for. A cell line that's unlimited in supply that you can infuse and get the results that you're getting. But the encapsulation is still an issue. And I could talk about the ViaCyte clinical trials. Jeremy, you definitely can. And actually, that's how we first met, was we talked over lunch just about lessons learned.
Yeah.
And it was really important for me coming in because I think that perspective is so precious as we develop clinical trials to understand the complications, the challenges to improve. Now, I think that's what we've learned, though, the complications and challenges. Challenges being location. So you're right. You could basically put it in multiple areas, but each area of our body has a different type of blood supply. So there's more, say, inside the body, in your, like around your stomach, inside where the intestines are, and the peritoneum, or the omentum, which is that fatty layer just below your belly. And you could have success there, but there's complications there. We've done, ViaCyte did subcutaneous, so just under the skin and the abdomen. And the things that were learned during that time was that our body is still very smart because it still sees a foreign body. And so it has a foreign body reaction. And that causes fibrosis around the capsules.
I would say that was my biggest learning from doing this study again, like 10 years ago, doing the first ones here. I'll admit, very naive. I thought, we'll implant these things and we'll cure type 1 diabetes from like the first patient. Like, let's go. And we started with implanting these in actually people's back. They're like kind of low back. And the reason we did there is that we didn't want them to be in the way if people were wearing insulin pumps or like CGMs in their stomach. We thought it would be kind of, out of the way. And after doing the first handful of patients, became very clear that these cells were dying as soon as we would implant them. And not because the immune system was mad at the islet cells in the device, it was mad at the device itself.
Yes.
And it would be like if I just took a credit card and put it in your back, well, guess what? Or a splinter, your body's going to react to that, kind of wall it off, et cetera. So there's a whole lot of work going on now in terms of, can we change the device, the material, the layout of it, how deep it is, the different pockets, etc. That's a big area of research. Can we modify the cells themselves to make them, kind of silent to the immune system, etc.? So all that's going on, but I think it's, again, like very helpful for listeners to kind of double down on this concept of the broad categories of, we're working on encapsulation, putting them in the device. But the things that people have heard probably in the news is these just kind of infusion of what's called the naked cells into the liver. And this does work in the sense that if the cells take up and they start producing insulin, there can be really, positive results. So maybe tell like our listeners about what that looks like when this works. Like, why are we going through all this problem? What have you seen in terms of patients, pre and post transplants that have actually worked?
I mean, the biggest take home would be off insulin, right? Like that's the North Star. And that's when it works. That's the only acceptable answer, is when you're off insulin. That works. And we've seen variations of that. You've seen it through infusion therapy with Vertex clinical trials that we've seen reported all over the news. And that's the goal. But it has to be not just initial treatment. It has to be longstanding. And that's what we're waiting to see. How long does this last? And this is so early, so we don't know that answer right now either. But the goal eventually will be to have encapsulation, because all these patients still need immunosuppression. Like, immunosuppression profiles are much safer now, but they have complications. And not everyone can take them. So it limits the population who can get the therapy. And if that's the case, then you want this available for every single person. And in order for that to happen, you have to have a safer way of getting those cells in the body. And that's going to be through some kind of encapsulation.
Yeah, well, the 880 study, which Vertex is still recruiting for, these patients have to be treated with immunosuppressants. But the modern therapy and the modern formulas, which is obviously much safer than the olden days, and what people that get kidney transplants go on. And I think the nice thing about that study is they just infuse it in the portal vein. But the other inclusion criteria, and maybe you can explain this, I think I know the answer, is patients have to have severe hypo unawareness. That just tells me that if you're going to go through this procedure and go on immunosuppressants, then you really need to have a functioning quote unquote beta cell that keeps you in a safe range all the time, that secretes insulin and glucagon when you need it.
Yeah, so that criteria really is it's from islet transplant, so from the early 2000s. It's kind of like the gold standard of how you start off these clinical trials for patients who have absolutely no adequate way of having the control they need to not have these acute issues with hypoglycemia that could be life-threatening. Now, that being said, it's also a regulatory piece that we've kind of forget to talk about sometimes, because it's actually how it's the FDA, the European agencies, Health Canada, all of these agencies are responsible for safety as well as we are, but they have to make sure that they have a very big barricade around the clinical trials for a very small population. And once you have some kind of proof of concept or it works, they expand that. And that's just kind of what this is. And also, if you infuse cells, you can't really take them back, right? Once they're in, they're in. So there's no way for it to be replaced outside of turning off the immunosuppression, and then our bodies would attack it. So the safety measure is that you get a very tiny population and see how they do, and then expand it, which brings us to encapsulation, because you can put them in and take them out, and there is no cell loss.
Yeah. Well, I think it's important for people that are listening, and maybe they're interested in these clinical trials. So first of all, just to be clear, like, these are not like approved therapies right now. These are still like in research. But I remember when we started the initial encapsulation trials with ViaCyte 10 years ago, getting calls and emails from literally all over the world. Hey, can I come down to San Diego and get some of them stem cells and, be fixed, like, kind of thing. So this is still experimental, and a lot of these, like, it depends on the protocol. You might need immunosuppression. If it works, it would be potentially like lifelong. So I think this issue with it's only right now being studied mostly in people with like severe hypoglycemia is because this is supposed to be kind of representing people that are, I hate to use the term, kind of quote unquote end of the road. They've tried all these other different therapies, like hybrid closed loops are not helping them out. So that's kind of where it's at now. And as these become more effective and hopefully we can limit immunosuppression, then it would be available to essentially everybody.
Yeah, and the other thing I want to ask you that relates to this whole technology is, I love the word CRISPR, because I think there's a drawer in my fridge for produce.
For vegetables.
And that seems to be a little bit of a promise. Maybe you can explain what that is to our lay listeners.
Yeah. So CRISPR-Cas9, you will hear that as well in cell therapy, but it's just it's a platform essentially. It's a company, CRISPR Therapeutics, but also a platform and a technology used to identify areas in genetic sequencing on the things that cause you to be immunogenic. So meaning that causes antibodies to attack your cells, and they're able to reprogram those and get rid of them. And they identify certain markers, and they'll get rid of them to see if that's effective in cloaking your cells. And that's basically it. It's a way to cloak the cells from the immune system.
So basically, it allows people to maybe get infused in the liver with islets and not need immunosuppressants.
Yes, that's the goal. So it's there's so many different companies working on different versions of this, but encapsulation, infusion, CRISPR-Cas9 technology, or gene editing is the larger term. There's different avenues, but I think I hope the listeners will understand that there's so many people working on it, but it's an inch by inch progress. It's not leap by leap.
10 to 15 years.
And again, like I always think back to when we started these trials, and again, the issue that we encountered early was that the device itself was a problem and would kill the cells. And I always said that if you asked me 5 years prior to that, like what would be harder? Taking stem cells and having them turn into islet cells and have them react to glucose and secrete insulin, or figure out something to put them in, I would have said, well, obviously, like the stem cells would be the hardest part. But we've actually solved that problem. We can create these cells. And now it seems like this seemingly insignificant but hugely significant issue of how do we give them back to people? How do we do that safely, efficiently, and ideally without immunosuppression? And so I think that kind of, when people ask you, what's taking so long? Like, how do you answer that question succinctly, I suppose?
I mean, it's a good question. And I, that's why I stay away from timelines always. I think if I had an answer for you right now, it would be that we have to get it right. So it's going to take time.
Yeah. Your pause in answering that question says it all.
Yeah.
And one thing I got from this podcast is that there's a lot of work being done in this field, all the different aspects of it. And you said what has happened in the last 5 years is tremendous. And Jeremy, his whole career is working on type 1, adjunctive therapies, prevention. So type 1 is hot these days. And I'm hoping that in my lifetime, I will see something that will help replace my destroyed beta cells. Those I don't want to use cuss words about the killer cells.
I know.
It's escalating. Your anger's escalating as the podcast goes
I'm not
on.
angry. I've accepted that.
Maybe kind of leaving people, if they want to learn more about some of the clinical trials or just general resources, are there places that you point people to?
You guys.
Yeah.
Always you guys. And clinicaltrials.gov. There's search categories. Look for cell therapy, diabetes. Those are the two things you need to put in, and you'll get the full list globally. I just also want to say that all of the clinical trials are ideas on paper. That's it. They wouldn't come to fruition without patients and people volunteering to do and participate in them. That is not taken lightly. So do your due diligence, ask the questions, talk to your providers, make sure you know what you're getting into, but also know that it's very much appreciated. I have never been more humbled by the people I have met and what they're willing to do. So I'm just really grateful, like I said, to be a part of this community and be able to talk about this.
We did a really good podcast with Jeremy's research coordinator on how to approach being a research subject, what questions to ask, et cetera. So that's out there, and that's a great point. Can't do it without the people. I volunteer Jeremy anytime.
Yeah, I volunteer. Steve Edelman, I sign him up for everything, every magazine.
He likes the devices in the back next to his back tattoo.
Yeah. Well, thanks so much for doing this with us. This has been great. I hope you all have enjoyed listening to it. Make sure to like, subscribe, do all those social media things for us. And, we'll catch you on the next one. Thanks, Steve.
Yeah.
Thanks, Manasi. Good seeing you.
Yeah. Thank you very much.
Guys.